So today's experiment is E by M of an electrons by Thomson's method. The formula which we are going to use for this today's experiment is E over M is equal to 2 into V into Y by ILdP square, where V is the applied potential voltage, Y is the deflection of light spot on the screen, L is the length of the reflecting plates, capital L is the distance from the screen, small d is the separation between two plates, and B is the magnetic field, horizontal components of Earth's magnetic field, and this K value, which is here in the formula ILD is nothing but K, which will be given on your apparatus. So our initial adjustments is gonna be like we are gonna align this magnetometer to the Earth's magnetic field, place this anywhere on the table, and we wait for this needle to settle down. And after it settles down, we just mark 2 points where it settles, like this, and then we use a long scale or some scale, and we draw a long straight line like this. Now what we're going to do is we are going to take this setup over here and align it onto the line like this. Make sure the scale is parallel to the line, and then we are going to introduce the magnetometer back onto the setup the same way. Now so now we are gonna align this to 0 0 by rotating this. Once it comes to 0 0, you can see that it's at 0 0. Once it settles down, what we are gonna do is so as you can see, it's settled down. Now we're going to introduce two bar magnets, and on the bar magnets you can see the south pole is written and the north pole is written. It will be written on the magnets, north pole, south pole. So we are gonna keep the bar magnet at some particular distance. Make sure it's at least 20 centimeter away from the magnetometer, such that the north pole just keep the bar magnets over here, and after that you take the readings over here. So you can see that over here right now it's about 25 degrees on one side, other side will also be 25 degrees. So that's how we take the readings on this. So I'll just show you how to take one set of readings. So as you have noticed, I've kept the bar magnets at around 21.5 centimeter, and correspondingly the magnet over here is a bit weak, so there is not much deflection, but the ones in the exam you get will be stronger. So if you take this side to be as theta 1, so that's the reading of this one, and this side to be as theta 2, or the second set of readings. So now theta 1 over here is about 10 degrees and theta 2 is also about 10 degrees. Now we will flip the poles of the magnets, and you can see some deflection over there. Keep it at the same distance, and again theta 1 is again almost around it's almost 6 degrees. Similarly theta 4 is also 6 degrees. So this is theta 3, theta 4. Theta 1 and 2 was when you kept it originally. Now we are going to interchange the magnets. So the right hand side of the magnet comes to the left hand side, and left hand side comes to the right hand side, and again at the same distance we take down the reading. So this will be theta 5, this will be theta 6. Irrespective of where the magnet is, once you decide this is theta 1, so all the odd numbers of theta will be on the left hand side, and on even numbers of theta will be on the right hand side. And for the last set of values, we again shift the poles, keep at the same distance, equidistance as the original, and we take the readings. So over here it's almost about between 8 to 10 degrees, so mean would be around 9 degrees or something. Okay, so the reason we have kept the magnets at such large distances because we need the deflections to be between 30 and 60 degrees, and always make sure that the bar magnets are at equidistance from the magnetometer. So over here it's around 21.5 centimeter. Now how to take the reading is this set of data is 1 theta value and this side of it is 1 theta value. And on the bar magnet, since we know that it has a north pole and a south pole, always make sure that both the bar magnets, the poles are always opposite poles are facing each other. So if this side is north pole, this side should be south pole. So we're gonna do 4 interchanges for this reading. So the first reading, let's say this side north pole is facing to the magnetometer, so this side south pole will be facing the magnetometer. We take them the readings. Next we are going to flip the bar magnets at the same position, such that if this side is south pole, this becomes north, and this is north, this becomes south. Now we are going to interchange the bar magnet. So this bar magnet comes over here and this comes over here. Take the readings, and then again we flip it back to again the opposite poles, and we take the set of readings. So for the second part of the experiment, what we're going to do is we're going to introduce the electric field over here. So we just remove the magnetometer and introduce this cathode ray tube again in the same position as that. Make sure that it's perpendicular to it, and we just connect this to this voltmeter slash supplier, and then we plug it in, switch on. Make sure this is in forward, and over here you can see that there is a green dot over here at the center, which means this is already it's already calibrated. If not, using the X shift and definite volts over here, try to bring it to the center. Over here is the reason it's showing 0 is because again the magnets are very weak and we have kept it at a large distance. So if we bring the magnets close, let's say this is for just demonstration purposes, just don't do it in the exam. So you can see that the shift is way too much, so it's almost like some 10 millimeters or something, 10 or 12 millimeters. Now we bring it back to the center over here, which is I think, yeah, this is at this center. And if you take a reading over here, you can see it's at 15 volts, 15 millivolts. It's at 15 volts. So since the magnets are weak and we have kept it this close, we are getting a reading. But the magnets which you'll get are going to be pretty strong, so keep it at this very large distance, and you take down the volt readings. And now the B over here, which is the Earth's magnetic field, is basically nothing but BH tan theta. The value of BH is nothing but 0.36 into 10 power minus 4, and tan theta you found out over here, so you found your B. And your E by M is basically we substitute back over here in this formula. So your E by M value is 2Vy by Kb square. So V is the voltage which you find out over using this, and then Y is your Y shift which you find out, and K is the constant which is written on the thing over here. So this is your constant value. It will be different for different setups. And your B square is what you have calculated, which is nothing but BH tan theta. And then you find E by M, which this should be almost similar. And that's your experiment. That's it. So if you're not able to see a proper dot like this, just try to change the intensity parameter or the focus parameter over here. And for by any chance, if let's say if your thing is at forward and it can't go up, just change it to reverse and try to shift using the Y shift. Now in this experiment, again we are going to use the same distances as for the magnetometer ones. We keep it at the same distances, same equidistances. And as you can see, when we introduced the magnet, there was some shift from the origin. So we count that shift from the origin and we note that as Y shift. So each unit over here you just divide it and see, it will be different for different apparatus. So over here it's almost like I think 3, yeah, it's like 3 Y shift, so it's almost 3 into 10 power minus 3 millimeter. And now what you do is we use the y shift to bring it back to 0, to the center back, and when it's at the center we take the readings at the voltmeter. Okay. So after we find the value of it by experimentation, we are going to find it using theoretical value, which is nothing but E over m. The charge, where E is the charge of the electron, m is the mass of the electron. Just divide that and you get the theoretical value, which is almost 1.7582 into 10 power 11 coulombs per kilogram, and that's it.